I figured it was easiest to do a screencast to kind of talk through different things instead of having to type it all out. So I kind of pulled up the question that you had put your first question mark on, and that this is just kind of trying to apply. You got the letters right when you looked at the matching part up here. You, I think, put CADB, and that is correct. So down here, you're just on the electron that's circled. Remember back when we used to draw electrons in the boxes with the arrows? You're trying to label that. So with N being the energy level, it's 3, because it's in the third energy level, the one they circled. The L is 2, at the sub-level. The ML, it could be many different ones because it's either -2, -1, 0, 1, or 2. It's just kind of which one of the boxes is labeled, but it could be any of one of those in those boxes, so it doesn't matter which number of those. And the M and the S is the spin, or it's one of two ways. So often, the arrow going up will give it a plus 1/2, so it's 1/2. Or it could be a -1/2 as well. Like, it doesn't matter which one, but that's usually because it's either going up or down, so there's two options for MS. Okay, so the next one that's kind of there, and yeah, they didn't talk about these, and I don't know why this practice kind of brings upon stuff that is not in the 2 lessons you did for this unit, but I guess it's just trying to pull in other things that it has learned, or supposedly has taught in previous units. So what causes specific lines to appear in a line spectrum? So line spectrum is it is electromagnetic spectrum in a sense of what's kind of the light emitting, or emitting the energy. So kind of the answer they're going with are different things. Electrons and an element absorb and emit energy in quantized or specific amounts that are characteristic to that element. So each element has kind of a specific spectrum that appears. Okay, so the frequencies or wavelengths of the photons, so light absorbed or emitted, show up as specific absorption or emission lines at the same frequencies in a line spectrum. Okay, so it's kind of the energy or something that is released, and that what's going on. Okay, so as you move down here, so we're going to match a little bit more of the terms with the definitions. So a prism, okay, prism is often that light, not a prism, what I'm thinking of, the kind of clear glass that kind of emits a rainbow of light. So the a prism is a material that splits light into its frequencies. Okay, that's for A. An absorption spectrum is the frequencies of energy absorbed by an element. Makes sense. Absorption, absorbed. Okay, we're looking at emission spectrum. Well, it's the frequencies of photons a sample emits emission. The flame test is heating a sample to identify its spectrum. So what you could do in a chemistry lab, and often this is kind of popular, is if you heat an element or with a flame, kind of see the flame of it, it'll emit the light kind of differently. See its spectrum. It's kind of neat. So each element's unique. And then last, the line spectrum is sorry, I skipped E. Spectrum is a continuous range of wavelengths or frequencies. And then F, a line spectrum, is specific frequencies of energy transitions in a substance. Okay. I think you had a few more questions. So the nuclear structure, this is kind of the new stuff this way. Let me double check. You had, because I'm pulling this up here, it's a little blurry, but I think, yeah, you had questions on the quarks. Yep. So each role of the following particles and the protons and neutrons. So what they've kind of figured out is that we thought that protons and neutrons were kind of the smallest kind of things, but then recently or later that they're figuring out it's more. So quarks are subatomic particles that make up protons and neutrons. Each proton and neutron is made up of 3 quarks. Okay. Gluons, okay, so what they are, so it goes back to the quarks that make up the protons and neutrons are bound together by subatomic particles called gluons. Think glue. Okay, yeah, that's probably what they thought of. The strong nuclear force acts on the gluons in the nucleus. Okay, so quarks are what make up protons and neutrons. Gluons are kind of what holds together the quarks that make up those things. Okay, so there's that part. And I think you had a few more, probably till the half-life. Yeah. Okay, so as we move on, so the next question, what forces are at work inside the nucleus of an atom? What keeps the nucleus together? So this was kind of mentioned a little bit, I think in one of the lessons, but electrostatic forces cause the protons in the nucleus to repel each other, because remember, if they're all positive, they're going to want to repel each other, like repels. So the strong nuclear force, so we call it, cause the protons and neutrons to attract each other. The strong nuclear force are much stronger than the electrostatic, so the nucleus doesn't split apart. So what holds it together is stronger than what's kind of the protons repelling. Okay. Now, what makes a nucleus unstable? So that's the next question. Which atoms tend to be unstable? So a nucleus is unstable when the strong nuclear forces do not balance the electrostatic forces. Atoms with high atomic numbers tend to be unstable. And this is kind of bringing about, like when we started about uranium and being radioactive and breaking down. When they get really large, it just can't hold itself together as well. And so once you get to a point that all the elements, even after uranium, and so they'll break apart. They're unstable, we would call that. So atoms with high atomic numbers tend to be unstable. Okay. What is loss in an atom as a result of radioactive decay, and what equation relates to that? I think this was mentioned in the lesson. It might have been in the first lesson of it, 10.3.1 or something. Not the one most recently about half-life. But anyhow, so maybe like 2 weeks ago. There's a loss of mass in the atom after the decay. Einstein's equation, remember that famous equation E equals mc squared, shows how that energy and mass are related. Okay? And then I think you had a little bit more. Yeah, the last little bit before you get down to what was kind of mentioned before. Okay. So, radioactive decay. So this really relates to that lesson that I just mentioned. It is definitely, if you go back to this one, 10.3.1, where it talks about the different radioactive decays, it is going, so which one, and this actually might have been one of my forms question, which one doesn't cause a transmutation, means a change, and it's gamma emission, by radioactive decay by gamma emission doesn't cause a transmutation. You're not getting a change in an element, it's just emitting electrostatic waves. Okay? Then next, you can find more examples of these. I want you to write an equation. So for like the first one, you're going to go to alpha emission, and if I can find it, so this is B, the radioactive decay by alpha emission, write an equation showing the decay. So if you go, and if I can find it, or maybe it might be in the second section. I'm trying to click through the nuclear fusion and fission. It's when it started talking about, so that was the equation I just told you, E equals mc squared. Trying to remember where it was. Here we go. Once my computer loads. So, I think, and it's going to be an alpha decay for the first one. It's going to emit a helium particle. So this is going to set you up the next one. Okay. So it's going to look like this, ultimately. What you're going to do is you're using a different element, for PO. So instead of uranium, you're going to put PO there. You're going to look, they gave you what it starts with, so 210 and 94, or sorry, 84. I can't read it. 84. So 210 and 84 with PO. Now it's going to break down, and it doesn't matter if you write it on which side, but it's going to break apart the alpha decay, and which it means it's going to emit a helium. So the next thing you're going to write is the He with 4 over 2. Remember how we find these? We subtract these over. So you had 210 minus 4, well, that would be probably 206. And then you're going to have 84 with 2, so minus 2, so it's going to be 82. Well, you need to figure out what element that is. So you'd go to the periodic table and look for element number 82, and that would be the symbol you're going to write right there, because it changes down to that. Okay? And then the next is very similar, because you're going to do a beta, so it's kind of the opposite. You're not releasing a helium, but you're going to be releasing an electron, in which this was shown later. Okay, so we're releasing a beta to K. Okay, so it's going to look kind of like this. You're going to start with your element right here, which was cobalt, and then you're going to write the electron, okay, and then you're going to kind of do the math. It's going to add a proton. You need to find out what element it's going to be. So it goes from 27, adds 1, so it's going to be 28, whatever element that is. You're going to put the name or the symbol there, okay. And then the last little bit, which I think you have as your questions. Yeah. So, if we look at the ones down here. So use that to answer the following questions. How does this reaction demonstrate the laws of conservation of charge and conservation of nucleon number? Okay, remember the charge of the reactants and the charge of the products are the same. There's nothing different about this one. And the total number of nucleons is the same as before as after. Because if you looked at, there's 234 over here, there's 234 because it's plus 0. And then down here is 90, and then you have 91 minus 1, which is they're equal on both sides. So that kind of shows that there's nothing that's changed on both sides, in conservation. And then down here, what is the binding energy of 1 mole of this? Is the mass defect is 1.908 grams per mole. Okay, you're gonna plug it into the E equals mc squared, with what you are given. So you're solving for E. Okay, you know the mass is 1.908 grams. Okay, and then you kind of have to figure out that you're changing the gram. You're going to go to kilograms. So 1.908 G times 1 kilogram divided by 1,000 grams. Okay, times the 3 times 10 to the 8th meters divided by seconds squared. Okay, so that whole thing's squared. Okay, you should end up, after solving for it all, of 1.717 times 10 to the 14th joules. Okay. C, you could look up, so if you find out what that is, but you just need to make sure about the grams. Okay, so look at more of solving for E equals mc squared, and that would help you a little bit. And I think that kind of brings you to half-life, okay, which I think you got more of on, and it's more of what we were talking about, okay? So if you have any more questions, please ask. I hope that helped a little bit with all that you're looking at.